parameter estimation in the context of risk-assisted systems. And we aim to solve this problem by employing tensor-based methods to reduce the complexity of the estimation of the parameters of a moving target. So this work was developed in the joint project between UFC and Edison Research. So this work was developed in the context of INCT systems. So in the recent years, we have seen an increasing integration between radar sensing and communication systems. And this integration between the both functionalities of the network is what is being called integrated sensing and communications. And by developing some works in this context, we aim to integrate both functionalities into a single network device. And by doing that, we aim to achieve higher spectrum energy efficiencies, while in the future also lowering the cost to produce such network devices. Alongside INCT systems, we also have the technology of reconfigurable intelligent surfaces, RIS for short. And the RIS and INCT technologies has an interesting convergence, an interesting synergy, because the RIS is capable of creating additional propagation paths between a base station and a user that is blocked. The user could be blocked by, let's say, some building, or the direct link between the base station and the user is too weak. So by deploying a RIS, we can create a strong virtual line of sight link between the base station and a user, or target. So in this context, this work aims to shed some light in the parameter estimation problem of a moving target. So we want to estimate the delay, Doppler, and angular information of a moving target. And as our baseline, we have chosen this paper by Erkan that was published, I think, 3 months ago. And in this paper, he proposed to solve this parameter estimation problem by proposing a design of a 4D optimization function and breaking it into 2D steps to solve the estimation of delay, Doppler, and angle. What we will do in this work is to go a step further and exploit the multidimensionality of the communication signal to break a 2D optimization problem into 1D optimization problems, lowering the overall complexity of the scenario. So in this first figure, just to situate everyone, we have a monostatic scenario, sensing scenario. So the monostatic has only one base station, and this only base station will act as the transmitting and receiving of the M-wave signal. And we also have another scenario with the transmitting and receiving not located on the same location. And this is what we call bistatic scenarios on sensing systems. The main scenario of this work is the monostatic scenario. So why using tensors? I think our colleagues have done a nice introduction on this topic, so I will go a bit fast on that. But basically, communication signals are intrinsically multidimensional. So by exploiting this multidimensional of communication signal, we can reach less restrictive conditions to estimate some channel matrices. Some applications of using tensors in communication signals are written here. So we can use tensor-based algorithms to estimate channels, to detect symbols, and also exploit the low-rank structure of some communication signals. That is the focus of this work. And by exploiting the low-rank structure of some signals, we reach a lower complexity computation to estimate the target's parameters. In this work, I'm using a simple decomposition, the parafact decomposition, also known as CPD. And the CPD can be viewed as a decomposition that can be viewed as the sum of rank 1 tensors. Here we have the outer product notation for the CPD. They are rank tensors in this case. But in this work in particular, we are considering rank 1 CPD. So we have only one outer product. And the CPD can be solved either by the alternating least squares algorithm or the high order SVD. In this work, we have chosen to solve the CPD by estimating it by the high order SVD. So this is the proposed scenario. So we have a base station transmitting an OFD impulse through a RIS to a target, and the target will reflect back the OFD impulse through the RIS back to the base station. So the base station will transmit an OFD impulse and we will receive its echo. The direct link between the base station and the target is unavailable. And also, the target's parameter, the delay, the Doppler angle, are considered constant over the total time window of this process. So we are not tracking the variations on the target's parameters. Regarding our contributions, we propose a low complexity sensing approach for this problem of parameter estimation. And this is done by exploiting the low rank structure of the received echo signal. Also, just to highlight something or some of the assumptions of the scenario, our base station is assumed to be multi-antenna, but we use only a single antenna to do this process. So this is the proposed sensing protocol, where W represents the RIS phase shift patterns. In this case, we consider that we have a repetition-based RIS phase shift pattern, so each phase shift pattern is repeated Q times. And this repetition composes a block, and we have a total of L blocks. So in summary, we have L different phase shift patterns repeated in Q times L FDM symbols. So that's our sensing protocol. This first equation represents the received X signal. So we are using a structure modeling. So we have theta, that is the angle that we want to estimate, the angle between the target and the RIS. We have the delay of the target, C of tau, and the Doppler frequency of the target, that is D of nu. So by exploiting some properties and stacking out the subcarriers and symbols, we go from this first equation to this second equation. And this second equation is the equation that we will use to build rank 1 tensor in the next slide. In this third equation, it's just a mathematical representation of the sensing protocol. So we can represent this repetition with the help of the Kronecker product between a vectors of ones. And now, developing our tensor model. So by exploiting the Kronecker structure of the received echo matrix, that is this one, this is the echo matrix. By exploiting this structure, we can recast the problem as this second equation that can be viewed as the tensor unfolding. I think it's the first mode unfolding of a parafact tensor. The unfold is just a matrix representation of a multidimensional object. So we have our tensor in here, a third order tensor. And as I have said, we have a rank 1 tensor, so we do not have a summation. It's just an outer product between three vectors. And the matrix representation, its unfoldings, are given by these three equations, that each one are rank 1 matrices. So our main goal is to exploit the multilinear structure of this signal, of this echo signal, and design a low complexity estimator. In this figure, we just have a visual representation of our model in this equation, in this tensor equation. So as we can see, it's just a single rank 1 tensor. We have just a unique outer product between three vectors. And now entering on the proposed parameter estimation solution of our problem. So our solution is divided in two stages. In the first stage of the proposed solution, we apply the HOSVD to estimate the steering vectors containing the information of delay, Doppler, and angle. Why we are using the HOSVD? As I have said, all these matrices are rank 1 matrices. So by employing the SVD, we can obtain an estimation of the subspace of these steering vectors up to a scaling ambiguity. So Taylor SVD, in this case, would be a good way to solve the problem. And taking the SVD, the left singular vectors of each one of these unfolding matrices, we can build the estimates of C of tau, D of nu, and beta of theta and nu. In this case, the angular information is coupled with the Doppler information, so we need a further process to remove the Doppler influence on the angular vector. So that would be the first stage of our solution. That would be these blocks in here. So the output of the HOSVD will be these steering vectors, and each one of them will later enter optimization problem to estimate the parameter that generates these steering vectors. So that's our second stage. So first, we solve two 1D optimization problems to estimate the delay in Doppler by solving a line search problem. And by solving this line search problem with these cost functions, we obtain the estimates of the Doppler and the delay of these targets. After that, we do a processing to remove the influence of the Doppler on beta of theta and nu. And then we apply this cost function to obtain an estimation of the angular information of the target. So that encompasses our solution for this scenario. This is just a pseudocode of the proposed algorithm. So we require a tensor Y, and the SVD is solved by taking the HOSVD is solved by taking the SVDs of the three unfoldings of this tensor. Then we build the estimates of the steering vectors. And after computing the SVDs, we then solve these three optimization problems, in which this step is to remove the influence of the Doppler of the vector that contains the angular information and the Doppler information. So now, analysis of the computational complexity of our proposed solution. This one on the left is the solution proposed by Erkan on his paper. And what I will call attention of everyone is this first term. This first term on red represents the complexity to compute the estimation of the delay in Doppler by Erkan methods. And what we are doing in this work is breaking this product by exploiting the separability of the tensor method to break this product into a summation. So instead of estimating the Doppler delay into a single cost function, we break this cost function in 2 steps and reduce the overall complexity to compute everything. So this first equation is how Erkan is doing the estimation of delay in Doppler. So as we can see in here, the delay in Doppler cost function have both the informations of the delay and the Doppler, while all cost functions to estimate the delay in Doppler are separated, which speeds up the process of estimation. And in here we have the cost function to estimate the theta. And we are using the same cost function as Erkan to estimate angular information. And it's a bidimensional cost function, since we have the angular information is composed of 2 components. So entering the simulation results, these are the simulation parameters of our scenario. So we are considering arrays with 16 reflecting elements. We are considering a total of 64 FDM symbols. And I am considering 5,000 experiments to take the mean of the performances. So here are the first results. So in the first figure on the left, we have the performance evaluation to estimate the the delay information, where the proposed solution are the green curves. So as we can see, our solution performs slightly worse than the proposed than the benchmark at the lower SNR range of minus 10 dB. But starting from minus 10 dB, our solution performs exactly the same as the baseline. This is true for both the delay and Doppler estimation, as we can see in these first two figures. But just to remember everyone, we are essentially breaking the complexity of the method. So we are achieving almost the same performance while reducing the complexity. And this last figure is the estimation of the angular information of the target. And since we are using the same method to estimate the angular information, we are essentially achieving the same performance as our baseline. Now, regarding the complexity analysis of both of the chosen baseline and our proposed solution. So, just to clarify what we are doing. So we are breaking this optimization problem on the left by exploiting the tensor structure of the signal into two optimization problems that are simple to solve. And by doing that, we are achieving a gain in performance of at least 10 times when it comes to the number of subcarriers, at least. And on the right, we have another evaluation of the complexity that is linked to the number of grid points to solve the optimization problems. These three blocks are optimization problems. So depending on the resolution of these optimization problems, our solution can be 1,000 times less complex than the baseline. So we are achieving exactly the same performance starting from minus 10 dB point, while reducing the complexity by a lot. So in summary, in this work, we have proposed the rank 1 tensor design for a Wiz-assisted sensing scenario, in which we are capable, by exploiting the rank 1 structure of the signal, we can decouple the estimates of the delay in Doppler. And by doing that, we solve the problem by the HOSVD and achieve a greater performance reduction of complexity. Regarding the ongoing research, I'm currently working with the extension of this case to the MIMO scenario, but for now, the monostatic MIMO. And in a few more months, I expect to complete the extension to the bistatic sensing scenario. Also, currently, the monostatic MIMO scenario that I'm working, I was able to express the received echo signal as a nested tensor that solves the problems of parameter estimation in also a two-stage approach. Passar aqui. Não tem que passar. Não, está travado. Pronto. Obrigado. Thank you for the attention, everyone.